Okay, so I'd like to introduce Acacio Cruz, another Googler. I had the pleasure of hearing him speak about frameworks previously. It was all good. This time he's going to talk about something that anybody who has spikes in traffic or needs to scale to handle that needs to handle, and that's load shedding. So without further ado, Acacio.
Hi everyone, I know that I am the last talk that stands between you and a beer, so I have that privilege. I've been an SRE manager and then later director at Google until about a month ago, and I just transitioned to a role in a new PA, new group organization on frameworks and production platform. Basically taking all of the work that we started doing skunkworks in SRE a few years ago, including what I'm going to be talking today, into a properly funded. This is not the death of SRE mission, it's just the vindication. Oh my God, what is it I'm doing there? I have no idea. Apologies, there's a bug in the system. So why are we here discussing load shedding? So this happened. In 2009, there were 3 outages in Gmail, and if you guys look at the name that is mentioned, so 3 outages, global outages of Gmail that were caused by, in one of them, augmented by, in the other one, or the backend actually died because of one small backend that really couldn't deal with the overload system. And then I took my first lesson, which is if you're managing large-scale internet service, the 15 moments of fame are not cool. Not, especially because I went to bed as very anonymous person. I woke up in BBC News, so thank you guys if BBC is here. So the time we had 3 global Gmail outages in 2009. As a compensation, the service that was involved in those outages was then given to me to fix. And then in 2010, we did a lot of mitigation, basically, making sure it doesn't go down again. And it did, but you guys didn't feel it. And then in 2010, we actually had our first load shedding implementation. It was very basic, I'll go into details later. And in 2011, we had something that was robust enough and generic enough that we actually could start generalizing, and we then applied it to several of all the services I was managing, and it went really, really well. And now, we've effectively, and this is the work I'm now doing, we actually standardize into plug-in modules that we can actually deploy across all the services at Google. We're now, and since I can't quote numbers, we're now managing XXX hundreds of QPS at Google. So we're going to cover 3 parts. The load shedding itself, the overview, the threads and principles, and then what happens to a service that actually has good load shedding. So what are the threats to a service? This is one of them. So when you get an intern and you teach him MapReduce, and then you add a data center, and then you have an intern-generated distributed denial of service. This is becoming less frequent at Google because we're becoming a bigger company, a more mature company, and controls and stuff. But for many years, there was the springtime, intern denial of service that was very common. So that's a typical one, but effectively, what are the threats? We have the single task overload. The single task overload is the most important one that it's often overlooked, but is the most important aspect where to do load shedding, because that is the little phenomena that causes cascading failures. Like if you don't tackle that first death, that's when a cascading failure. Cascading failure is nothing more than a sequence of individual deaths. So you need to handle the task overload. At Google, we also have a specific scenario where we have multiple clusters, and you can have one cluster that is overloaded while the others are not. Typical example is the intern that runs a MapReduce on a specific cluster, not realizing that 10,000 machines is actually a pretty large number of machines. And then we actually have the other case, and we have this, which we have a whole service overload. The 2009 outages, one of them was started as single task overload in one of the failures in Gmail. We had a 0-day bug that started killing tasks, and then that generated a cluster to be overloaded, which then led to a whole service overload. So, principles of load shedding. So this is very common. People talk about is, the hockey stick curve. And the reality is actually slightly more complex. A task, if you actually measure in it, you guys probably know, Google is, pioneered the world with containers. We have jobs that run inside those containers with CPU reservations. What is less talked about is that when a task exceeds its container CPU reservation, it's put to death, right? By not immediately, there's a certain, flexibility, but effectively, there is a total lot of capacity. That's when it's inflicted by the cluster agent, but even when the cluster agent is actually not enforcing basically death, the tests themselves crash under load. The performance curve actually gets really, really bad. And, high latency is the death of a service, but infinite latency is way worse, and this is what an outage is. So at all costs, you need to avoid that scenario, because that's what it leads to, cascading failure. So principle number one of load shedding is you must survive. Survive under adversity, survive under hardship. And how do we do generically do provisioning? Services have the daily traffic coverage. In some services, it's so predictable that, for instance, I remember when Orchid had an outage and everyone panicked, and then everyone realized that what happened was the World Cup final, and you could see the dips in our systems that do prediction traffic. I couldn't cope with this human-generated event, right? So it's very, very predictable. Search, Gmail, all of our services are very, very predictable. Humans are creatures of habit, especially at statistical levels. So what people do, SRE does, is we provision and then we put the margin, right? So if you think utilization, the line is 100, and this goes to one of the questions that somebody asked Ramon before. What is how hot do you run your service? This has changed at Google, but we always had that margin. When I joined Google, the margin per cluster, per this, per that was 25%. So you can see, and then of course the tasks run below that. So you can see that utilization was not that high. But one of the things that we actually learn with time is that not all requests are born equal. If you have, typically a web-based system, if you're doing async refreshes, if one doesn't happen, the user is not going to notice. And one of the global outages was in Gmail was that we had a context widget that, because the backend had died, the whole Gmail interface failed to load, right? So that is what we now call nowadays a shareable traffic. What is the main application? Let's load that. That is critical. That is what the user must see. But the context widget, it's good to have. The context refresh, for instance, that's something that can happen in 5 minutes. And by the way, that batch traffic can also happen later, right? So this was the second cornerstone that we actually gave us a lot of flexibility in how to implement load shedding over the last few years. Going from all traffic is the same and you must survive, after a certain point you share traffic, but then when you have this dimension, then you have discretionary decision making on how to apply load shedding. Because when you have an outage, if you think this from a statistical point of view, in some cases, like if it's a software bug, there's not much you can do if the software itself dies. But if it's an externality, if it's a cluster that died, for instance, I was on call when one of our Munich data centers lost AC during the hottest summer in Munich, and machines actually melted. I had 2 minutes between getting, problem in the data center and actually Gmail is down, and machines melted. So what happened was we had X capacity, and then suddenly we had X minus Y. But there's still some capacity in other clusters. So it's not a complete outage, it's a partial outage. So your capacity from a statistical point of view, think about these numbers, you had a black bar at the top, now you have a red bar. So what are you going to do, right? If you don't have request priorities, you have very little tool, but you have request priorities. If you can characterize your traffic, then you actually have stuff to do. And basically what we do is we drop stuff that you don't miss. So the principles are, we distill this in about 7. So the first one is what we call sustained peak performance. Don't die, keep it there under pressure. This actually is more complicated than what it's being described here, because, for instance, one of the problems that we had was when Oracle/Sun helpfully changed the socket connection code in the JVM, and then they had a exponential algorithm, which is fine if you're handling 20, 30 connections, but if you're handling thousands, things are not as good. And we actually had a problem with the JVM. But this was too early in the stack for us to do anything, and those tasks did die. The only thing we could do there was basically revert that JVM build. However, most of the times, we are able to intervene before the task goes really into processing. So at that point, we actually have the decision, should I handle this traffic or not, right? So, and we can actually gate, so maintaining peak performance. There's a whole set of topics come to this is how do you know you are at peak performance? How do you know what is the task load? Second is isolation. It's very important in some scenarios. This is not a common need. It's a common need, but it's not a universal need, that some services, have different customers. And it's very important for us that if you have a customer that is misbehaving for some reason, that the others don't suffer. This can be generalized. One of the things that has come across is if you have paying customers versus non-paying customers, right? You want to make sure that the paying customers are not impacted by, a guy in university running a subscribe script to all of their mailing lists, hypothetical scenario. So request QoS is very important. I mentioned before, able to prioritize your traffic in different bands is important. Even if you only have 2 bands is already much better than having none. In our case, we kind of discuss how many bands we actually need. Word conserving. This is something that over time became more important than we knew, than we expected, which is called word conserving is if you're going through the process of calculating load and load shedding and throttling and all of that, and you come to the decision that particular request should be throttled, but for whatever reason that task is still not overloaded and can still fulfill that request, serve it. Right? Costs nothing. It's there. What he did, this is so basically fail open. This enabled us to do a lot of things that we weren't expecting, specifically because traffic sloshes around quite a bit. And if you do strict enforcing of quotas, sometimes what you have is drop traffic when you don't need to. So if you can, do it. So another thing is we learned a lot, and just to correct Ramon, who was just here, always do capacity planning in QPS, erase that. Always do capacity planning in CPS, cost per second. Because, and I give you an example, when Google was formed, search was the product. and search queries because the architecture had a very uniform cost. So the variance of the most expensive and the most cheap request was very little. So, you know, quantums, they're all the same cost, you know. But when we start dabbling into Gmail or lately into social, if you ask for my friends order by Affinity, I have no friends, so it's very cheap. But if you do the same thing for Lady Gaga, and she uses our product, you know, it's actually hard to sort 10 million followers and give them a you know, cost base. So a single query, same request, same type, same service has very different cost, and it's still 1 QPS. So we actually had to deal with high variance of services. And by the way, this is one of the reasons why max in-flight requests approach doesn't work. Because, you know, one request can actually kill one task, and in some cases 1,000 requests don't have the same cost of one request. We do have services where the cost variance is 5 orders of magnitude for the same query. Another aspect of you know, load chatting we've done is retries. We count on our, and you probably know since in papers, we have an RPC-based application architecture. We count on the client to do retries. The question is how to do retries. There's stuff that you should retry, which is basically task overloads. There's stuff that you should not retry. For instance, your service is over the backend quota. So, you know, having a careful implemented retry mechanism is very important, because otherwise you end up actually causing a further outage. You know, it happens a lot that a service that has not implemented client retries correctly overloads the system for some reason, the backend for some reason, or another event is overloading the system, and then the clients actually pile up requests, you know, with blind retries. And this can actually kill a system. So another thing that we actually did was we decoupled policy from mechanism. Policy, basically, here is how we implemented, is how do you compute load, how you do compute throttling decision, how you do all of this, and basically how you come to the verdict. And then, how do you actually implement the verdict? So we've been able to decouple these two things. In the beginning, our first implementation was just a bundle of code, and then we decoupled. What this allowed us actually to experiment with different policies, different mechanisms as well. So we are keeping on evolving. So just to iterate through, first one, survive, sustain peak performance, right? It's more important to survive than actually sustain performance. In real world, we actually see the tasks, and this is something that we actually leave. So my team actually does the software, and then actually the service owners implement and tweak the parameters. It's a risk, you know, it depends on what you want to do with the service. Some people like to run the service really hot and suffer the latency. Others prefer to have a little bit more margin in terms of what are the limits. But the most important thing is the task must not die. So the other one is isolation. This is something that really is impactful, as I said, when you have specially agreed per customer. One of the things that we do is actually by default, in the services that have many clients, we give default quotas, even if it's small, it doesn't really matter. Effectively, it matters like 5 customers matter. All of the other ones don't really matter. Request QoS I mentioned as well. We now have 4 bands. What is really important is well-defined semantics, because otherwise, what happens is the developers of the clients of the services that are have to characterize their traffic, they'll put all of their traffic as critical. Right? And then you start a race to the top. So one of the things that we actually have done is in one of the services was the pioneer using this. We said you need to categorize at least 30% of your traffic as something else. We don't care what. That forces the question, it forces the discussion. In the end, it's variable, but it's something that they have to do. We have a mechanism called census where we do the propagation. So this is an important part, is we tag at the top of the call tree, and then that information is actually tagged. So right now we have a mechanism that allows to, from your click to storage, that request priority is trickled down through the stack, which means that we can, at any level, we have a throttling mechanism that actually is fair compared to the original traffic request. Work conserving, I mentioned, if you have spare capacity, serve it. Cost base, again, I mentioned this a little bit before. In some cases, which are very meaningful, query rates are meaningless. We've had in the system that Ramon, was talking about, which I managed before, by the way, was the system that I actually was managing. We used sometimes to have micro outages with 8 kps because a specific request is very expensive, where other tasks could do thousands without having an outage. So the cost is actually way more important than the query rate. Retries. Retries for Tasko is overloaded are very, very powerful, because if you get a very fast reply from a backend task saying, I'm overloaded, try it again, your latency impact is, very, very low. If you're in the same cluster, you have a round trip, 2 milliseconds. And that is a latency hit that most applications can eat without the user seeing, even if it's multiple layers of this happening. Right? There's a white paper by Jeff Dean, where he talks about hedging, right? Where you do basically 3 requests staging time. This is something that my team is actually implementing as well. We have implemented in the client side, which then makes this even more powerful. The obvious problem there is 3x cost, if you're not careful how to implement, but there is something very powerful. But very poor retry logic can actually be catastrophic. We just had an event where a service went from X to 32x of traffic because the client retry was not implemented correctly. So we actually have 2 areas of focus, right? We have the server-side throttling, which is where I'm talking mostly, and then we actually have the client side. One of the things that was presented this morning was the OSVisser. That's one of the areas. And client-side self-throttling is an area that is quite interesting, because it's an area where there's a symmetry of information. The more information you have on the client, the more sophisticated can your system be and be targeted to your application. But there is one thing that is very relevant that you can always do, regardless of what is the mechanisms of the client side, which is traffic prioritization. If you simply tag your traffic, if your request system or RPC system allows it, do it, even if you don't know what it's there for, because then the server side can use it as a hint in case of overload. On the server side, it's more interesting because you always have to do it anyway. And a lot of people think, oh, this is Google, just large scale. But even a smaller company is very vulnerable to a hacker, right? And it's way easier to overload 10, 20, 100 tasks than it is to overload, X very large number of tasks. But it still happens, and it's actually more catastrophic to your business. So, being able to actually survive and serve traffic, and potentially one of the things you can do is serve traffic from a certain, for your paying customers. It's a good mechanism to have. So, techniques. I know I'm speaking fast. I always speak fast. So this is a typical application layout at Google. We have a Google front end. Then there is a thing that we loosely call an application or a service. At Google, it's multiple layers. There's RPCs between all of these, and then it calls a backend. That backend itself can be one of these boxes, and turtles all the way down. At each layer, Google, we have a load balancing accounting system that gets reports of load from the backends and then feeds to the client. These have every single layer. Most companies do load balancing at the front, and then the stack underneath it is basically align. We don't do this at Google. Every single layer does both load balancing and then throttling on the task on the server side. So going back to the point that I made before, you want to load shed when your task is loaded, but how do you know your task is loaded? A non-trivial problem. So we actually started with a synthetic model. The first model, we actually went to monitoring, calculated exactly what were the costs in CPU. We measured, we had it in modeling system, times number of requests in flight versus the request type. And we actually made a mathematical model of the requests, and periodically ran it. It was very maintenance heavy. It was not accurate enough. However, that stupidly simple approach was already orders of magnitude better than not having it. And we were able to increase right there not having global outages. So that was good. And then we've been experimenting with multiple ways. One of the things that is important for us, we actually got a mechanism that we actually track, and this was somebody in my team that implemented very low cost counters in the JVM. So in Java first, and then it took us 2 years to replicate this in C++. We know the in-flight request cost per request. So as soon as a request comes into the task, we have some context data, and as the request flows through the task and sends requests to the backends and back, we actually have an ongoing account. So we know the CPU cost that a specific request is having for all the requests. So this is super powerful. So, but not always. One of the things that we actually found out is, for instance, in JVM, you have a non-correlation of the actual task load with the task of requests, garbage collection. Another thing that is very interesting for us to find out was what we call antagonistic workloads. If your task is running on the same machine where there's the intern map reduce, it's very bad if it's CPU intensive. It's even worse with the advent of hyper-threading, because now it's competing with your CPU cache. And we see, for instance, I don't know if you discussed this in other sessions, but there's a platform variation, performance platform variation, which is decreasing because Intel effectively is reaching the ceiling of performance of silicon. However, if you are in hyper-threading and sharing or competing for the CPU cache, you can actually have in 2 different machines with the same architecture variance of 30–40% performance. So you can't actually rely on your pre-computed cost or performance characteristic of your machine or your platform. So we need to measure all the time and survive, right? Because if you don't do that, what happens is either you put the 30% into your provisioning cost, costing you 30% CPU all the time, or you go 30% above your reservation and then you die, right? Or latency. So we actually have now different load trackers, one for memory utilization. Some people are more load sensitive, memory load sensitive than CPU sensitive. And the interesting thing is that we actually now combine all of this. We have, by default, we combine all of these load trackers, and we have some heuristics that basically give us the verdict of, the task is loaded, do something about it. So think about 1.0 as the task capacity, and this capacity is variable, is basically what you said the CPU reservation can be. And we set high priority, low priority thresholds, and then the higher priority has a higher threshold as expected. So very simple mechanism. The check is entirely local in the task. It is very fast, so we don't call out every time there's a request. Otherwise, this would be impossible. So even when we are collecting data from outside, we have an accounting system that does for the aggregate capacity. It's done out of band, right? So we make a local decision that might not be completely accurate, but doesn't matter at that point. Retries, if the task is overloaded, it's very important to shortcut and throttle the retry, because what happens is the client itself at the micro scale is actually rebalancing the traffic, if you think about it. The client is connected to multiple backend tasks, so it's basically doing some sort of balancing. At the macro scale, there's that load balancing mechanism that I mentioned about, but that's macro. This cluster talks to that cluster with a certain capacity. It does not have the agility to actually figure out that out of the thousands of tasks, there's 3 that are overloaded because there's an antagonistic task that they're running on the same machine and should be directed. It does not have that. So this actually means that a lot of the latency that we saw by 1 or 2 overloaded tasks disappears. We see what we call tail latency shrink by orders of magnitude. Custom isolation, one of the things that we really got into is actually blocking unexpected spikes. Unexpected traffic, when it arrives both unexpectedly and usually very fast. It's never a slow ramp up, because it's usually either a bug and push and then it gets triggered, or a load testing, and it's always very damaging. And because the system that do flow control and the load balancing, they always have a window of update of tens of seconds. Those systems can actually bring and divert traffic away, but they're never fast enough. So basically, load shedding guarantees that you survive those 15 seconds, those 20 seconds. Because if your task does not survive those 15 seconds, by the time the load system diverts some of the traffic, it's too late. Your cluster is down. And also, it needs to be out of priority aware. Work conserving, it's basically the mechanism I mentioned before. If you go through all of the decision and you come to the conclusion that yes, that service is over this quota, but is the task okay? Can you still serve? So serve it. So effectively, we have several thresholds. We have soft limits, hard limits, and the logic is there for those that are going to implement something after this talk. If we are below a soft target, it's a very cheap decision, always serve. If the task becomes loaded, and those are the parameters I mentioned before that we allow the teams to tweak, depends on their risk. If the user has quota, then serve it. And then if the user does not have a quota and it's loaded, then don't serve. Questions from the end? Okay. So impact and service management. So one of the things that we saw was one of the service that I was managing was the first service had 25% realization. So remember the bar at 1%, 100%? This was the service that was causing outages. And because it was so spiky and unknown and had already caused 3 Gmail global outages, we were very conservative. So when we picked up this service, it was 25%, which sounds bad, looks bad, but surprisingly was not that far below average service at the time at Google. That service has RPC types that have a cost variant of 6 magnitudes or more. In fact, we count from 0.1 to 10,000, and we stop counting at 10,000 cost because it's irrelevant. We think Lady Gaga's queries are around 1 million, so that's not good. However, that service, and it's unintended, was a service that was built to be around 3 nines, just because of the nature of the service. And without us actually intending it, it's now running 5 nines, sometimes on clusters, and it's mostly because of storage system. We're going to talk about the paging later, but the biggest impact is actually in utilization. We now run this service at 80%. In fact, now it's 85%. And it's hard to run a service at 85%. We have teams at Google that have done this in other areas of the company with search index. It's brilliant work, but requires many years of engineering, we didn't do this. On this particular service, it's very old code, it's very bad code, I have to admit, but we just throw a few million of QPS into it, and it's actually running 80% reliably. And the core component was we avoid cascading failures. The task will survive. So that was the first case, reliability and utilization. The second one is actually more complex. It took us a while to crack this one, actually. Batch workloads are very different and they're very spiky. It's a MapReduce that runs every day, that's in there, but then there's ad hoc stuff. Somebody wants to change a field in schema. Then it's in this different cluster. It's very hard to figure that out. But then it needs to be provisioned. We used to handle this differently, but nowadays we actually have to provision capacity. What happens there is if you look at all the white that's around those black areas is wasted CPUs that are reserved for and they're not being used. That costs a lot of money. At the same time, we have a nice service that is doing stuff. And it also has its own reserve margin, and it has a lot of white around it, which is costing a lot of money. So what if those two could be merged, right? So that's one of the things that we've done in that specific service, is to merge batch and production provisioning. And what we do, a precondition for this is actually making sure that all of the batch traffic is tagged as batch. So we know that a backend, can handle that traffic and will dump it. If it's under load. That has some very nice properties. First of all, there's a very interesting financial property. It saves a lot of money. But also, from an operations point of view, we always had this problem of having effectively two stacks to manage. Have the production stack, the batch stack, we have the margin. We actually literally had people that spent every week a few hours going 5% more there, but that batch traffic, so shoving machines from one to that work is gone. And now, if you actually can see, you have 2x margin, safety margins, from the two production allocations, provisioning, that can either be reduced to a single one or completely eliminated or added to extra safety margin. But usually what people do is get rid of one of them. So just a net saving altogether. So the batch handling is something that is really, really important for us. We're still going through all the services because it requires all the batches systems to actually tag their traffic. But specifically on SRE operations is a much simpler architecture. You don't need to maintain two serving pools. On product level, some of the things actually surprised us. For instance, you can, once you have these mechanisms, if you know, A, that your service will not die, B, that you actually have different types of traffic, then you can start doing interesting things. You can start designing your application that way, to take that into consideration. You can be way more aggressive in synchronous refresh stuff if you want to, because you know that is not going to hurt your prime application. Or you can do things like provision below peak traffic, right? You have that curve, you have a line, you don't have to buy all the machines for that. Or you can do a launch where you have a high variance of estimates. You don't actually know if your product is that popular as that PM says. So you bet that it's not going to be that popular and still not die if it does, really be, as popular. So you don't have failure by success. Always a sort of failure. That is very interesting. On operations, we do have one really big impactful thing. We used to have outages and people running around to their machines, getting a page, and they're not mere problems. And recently, we have somebody that actually decided to do a load testing in Maps, which is a fantastic product. But when you run load testing in Maps, just because of the scale of the product, there are no small load tests for maps is always big. And when you do it on peak, it's probably not the best time. And that generated a significant amount of traffic, which backend systems struggle with, except those that had load sharing. And what happened there was a nice conversation about why you're doing this. Have you thought about doing this off-peak? Turns out it was a bug, but it was a non-panicky because all that traffic was being shared away. Instead of managers escalation and outages we will custom what we had to 3 days to leisurely go through that. Turns out they actually had a business logic bug, and it went away. So the key message is it decreases the severity of events so that we don't have the 15 minutes of thing. Questions? While I slightly gloat. No questions?
I've got a small question. When you're trying to stop some batch process from the CPU, did you always try to kill it or try to freeze it for a while in perspective that 90% of its job is already done and not to spend time to redo it again?
Okay, so that's a good question. So most of the times at Google, you don't have access to somebody else's batch. Like most of the time, the batch job is not yours, so you actually don't have the privilege. You can do sudo, cluster management. Please kill this job, but usually it's considered to be an aggressive move. So in the old days, yes, we would actually panic and kill this and escalate to that team to please kill this job. Nowadays we don't care. We literally do not care. That the service will shed traffic, and what happens is what I try to explain there. So if it takes an hour minus the capacity that we are shedding away, takes an hour plus 15 minutes, it's not our problem, right? So if you can, we got to the point of confidence that you literally do not care, So then it becomes the person's problem of, does he really want the thing in 1 hour or can you wait 15 minutes more? If he can't wait, then there has to be a capacity discussion. If the workload can be deferred, because as you said, it's going to be done anyway and it's almost done, then nobody cares.
Okay, thank you.
Hi. I had a question regarding your provisioning of CPUs. So you mentioned that...
This?
Yes. So the reservation, is it actually 100% CPU for your hardware or your virtual server, or is it just below that? Because what you pointed out before is that in hardware, when you're doing hyperthreading, etc., there is a point at which, even if you run at 100%, you're actually causing more conflicts. Mm-hmm. So is your reservation done at the server level, or is it done at the, and if it's done at the server level, is it actually 100% or is it less than that?
So we use containers. So effectively what I'm talking about here is the container reservation. This is the ceiling of that container. So if you say a container is going to be 2 cores, that's the 100% is 2 cores. Mm-hmm. What the machine has, it depends, because our cluster manager, basically, if you think about a job as a collection of Lego bricks, all of the same shape, what the cluster manager does, goes through every single machine, or all of the cluster, and puts bricks to the maximum of that, machine capacity. So in some cases, the machine is fully booked. Some cases, the machine is we don't know. We don't know, and supposedly we shouldn't care. It got more complicated with, as I said, hyperthreading, because you suddenly before, we actually would have the CPU exclusively. Let's for a flexible value of exclusively. But nowadays it's more complicated. So there's things that have to be done. For instance, in Linux scheduling to make sure that when you say 2 cores, are the 2 cores in the same die, right, in the same package, and then you're not competing with someone else. It's complicated thing. I'm not the best person. There's a cluster manager, SRE somewhere that can delve into Borg, which is now a public name.
Thank you.
No worries.
Why don't you disable hyper?
So the question was, why don't we disable hyper-threading? Very simple answer, money. No, I'm being glib. There's money, but there's also, the first reason was, we actually first deployed the machines, and please, there's people in the audience which are Googlers that are way better than me to answer this question. But when Westmere came out, I think it was the first architecture where we did this. We actually did not have hyper-threading enabled, but the performance variance was so high, I think it was 60% faster than the previous generation per core, that it was seen as an equalizer. And then, not all jobs are memory bandwidth intensive, right? So then it's less of an issue. Any more questions? I'm going to be around until Wednesday. If you guys like to chat, please. Thank you.
Thank you, Acacio.